What we're going to do now is we're going to start talking about some very advanced template optimizations called template specialization. And this is in my 2.4 folder in the S-02 folder, part of my C++ STL repository. So basically, we've talked before about function overloading, where you can have different functions and you can have a generic function, then you can specialize the generic functions in order to get specialized functions, and the compiler will choose the specialized versions when it's given a choice between the generic function and the specialized function. So if you recall, when we talked about C++ function templates, the concept of function template specialization, or just function overloading, was very important. Turns out you can do the same thing with class templates as well. And what you can do is you can have a generic class, and then you can come along and specialize it for different types. And when given a choice, the compiler will always choose the specialized version. And that allows all kinds of clever optimizations to be performed. Now, it turns out that you can explicitly specialize a whole bunch of things. You can specialize function or class templates. You can specialize member functions of a class template. You can specialize static data members of class templates. You can specialize member classes of a class template, or member function templates of a class template, or member class templates of a class template, et cetera, et cetera, et cetera. And basically, you can specialize pretty much everything. And the way this is done is by sort of a weird syntax. You put the word template and then less than and greater than, and that's used as a prefix to indicate what follows is going to be a template specialization. And we'll take a look, and I think it'll become more clear once you look at an example what the heck is going on and how it works. So the first thing we're going to do is we're going to go over here and take a look at our container header file. And this is pretty much identical to what we just looked at. So we looked in the previous example at the container class. I think the only difference is I lowercased c instead of uppercasing the c. And so I have this class template that has a constructor that takes in a const ref of the parameter, and there's an increase method, and there's a private data member called element. And if we go look at the implementation of this class, you can see it does pretty much what you expect. It goes ahead and initializes element in the constructor, and the increase method does a plus plus on the element and then returns the plus plus. Okay, so far so good. Now let's come over here and take a look at some specializations of container. So here's an example of a specialization of container, and you can tell it's a specialization because it starts with template less than greater than. And we're going to call this specialization a container that's parameterized or specialized with a character star. That's pretty funky. And you're going to see that this is a really interesting example. This is the kind of thing you could never get your compiler to do normally if you just had the generic template. But when we use template specialization, we can do all kinds of cool magic and take full control over the behavior of this specialized version. So you can see down here, the constructor doesn't look a whole lot different. The constructor is just going to take a char star, and it's going to stash away the argument in the char star parameter. So we've done a specialization of type T from container, which was type T, and now we've specialized it to be char star. But the other thing we do here is completely different. Instead of having a method called increase, which is what we had before, now we're going to give it a totally different method altogether called uppercase. So in a sense, if you have a char star, which in our case is basically a string literal, increasing it now turns into uppercasing it. So you'll see how that works in a second. It's really cool. You would not have been able to do that with the generic definition of the template. We had to specialize it and then actually change the name of the method altogether. Here's the implementation of the specialized uppercase method. You can see we iterate from I equals 0 while we haven't reached the end of the string. And if it turns out that this is a lowercase letter, then we go ahead and we uppercase it. And I probably should probably update to use the C++ macros for all this stuff. There's some little macros or methods that do all that for you, but I just wanted to show you that kind of the full-blown version. So that's what uppercase does. It's going to uppercase the contents of the string. Then we're also going to talk about something called class foo later. I'm going to skip over that for the moment now and just show you the first part of our main program. So you can see we come down here and we define ourselves a container of int, which we give the value 7. That uses the generic non-specialized version. We have a container of double, which also uses the generic non-specialized version. My int gets the value 7, my double gets the value 10.5. And then just for kicks, we're going to make ourselves an array of characters that has the name hello world in it in lowercase. And then we're going to go ahead and make ourselves a container of char stars, and we pass in the lowercase string. Now this version, of course, because it's the container for char stars, is going to go use this specialization. So it's going to get this constructor, which is automatically synthesized, and it's going to get this implementation method, which will also be created. And then when we go ahead and call these methods, and I'll just show you this so far, when we say my int increase, my double increase, my char string uppercase, we're of course going to get the results being 8, 11.5, and hello world, all in uppercase. So all of those things are examples of how you can use both the generic versions of a container using the classic C++ template instantiation mechanisms, as well as take control over certain data types. In our case, a char star, which is very non-traditional for using for templates. Okay, now an interesting question is let's go back to the increase method here, and ignoring the specialization for char star for just a moment. For the int and the double, you'll notice that increase calls operator plus plus. So what that implies is for this code to work, we need to have operator plus plus defined on our data type. Whatever data type is used to parameterize this thing had better have operator plus plus defined on it. So to help illustrate this point, let me go ahead and show you class foo. So here's a foo, and we're going to be able to conditionally turn on operator plus plus or not. So this is just for illustration purposes. Class foo takes an int, and it stashes the int away, and it defines operator plus plus. And you can see when operator plus plus is called, it goes ahead and prints out the fact it was called, and then it increments the count by 1 and returns a new foo that has been incremented. So that's operator plus plus. And then we also have a way to convert a foo back into an int, very much like how your assignment number 2 works by, in your case, you'll have operator bool. In this case, we have operator int. Okay, so, and then down here, we have an insertion operator that takes a foo and converts the foo to an int and then prints it to the output. All right, so far so good. Let's come down here and take a look at the code. So here we're going to make a container that's instantiated with type foo, and we're going to pass in a foo, which is given the value 10, and then we're going to call foo, my foo increase. So let's go ahead and run this code, and this will also show us what the other stuff does. And you can see the output is pretty much what we would expect. We got the stuff up here, we get 8, 11.5, and hello world. And then down here, when we do the foo, it'll call foo increase, and that'll call foo operator plus plus. Okay, now here's the interesting question. What happens if we had instantiated the container with a foo that didn't have operator plus plus? So let's just go ahead and comment that out. Let's say if 0, which is the easiest way to comment stuff out. Okay, so now there's no longer an operator plus plus defined on foo. So what's going to happen? Well, if we come down here and we look at the code, you can see all of a sudden this guy, whoops, down here. Oh, and let me also get rid of this specialization too, because I want to show you that in a second. So let's pretend like that's not here for the moment. Okay, So now you can see what I was trying to evoke, which is when the increase method is called on my foo, it's going to complain and say, we can't instantiate that because there's no way to increment. There's no built-in operator plus plus to increment it at all. So the code won't compile. So what we're going to have to do is find a way to fix that. And what you can see up here is the way to fix that, of course, is to do this and actually bring that guy back online. So now if we come back down here, you can see that we now have a foo that has operator plus plus defined, and therefore increase, which comes from here, will be able to legitimately call plus plus on the foo that was instantiated with it. Okay, so that's kind of cool. So now let's go one step further. Let's go up here and now let's explicitly specialize foo. Oh, and before I do that though, let me go ahead and run the code to just show what this version looks like. So this is the version that does not have specialization enabled, but instead is just going to go ahead and use what's built in. So when this runs, you can see it says foo operator plus plus, and that of course comes from here. So now what I'm going to do, just to kind of flesh out the whole thing, I'm going to come along and I'm going to define myself a specialization of foo. So before we used the generic version of foo that was instantiated from container. So we use the generic version of container that was instantiated with a foo. Now we're going to define ourselves a specialized container that is explicitly instantiated or specialized with foo. So this is going to be the new version. And as you can see, it's going to look very much like what we looked at before. You notice how we can change the parameter type if we want to. So before, container took in a const t arg, and down here we can actually change it just to take an instance as opposed to a const ref, or we could change it back to const. Either way will work fine. The point is you can change it. That's the main thing I want to show you is you can change that. And then down here, this is the new increase method that gets called. That's going to print out the fact it's being called, and then it's going to go ahead and basically call the plus plus operation. And that, of course, will then call the plus plus operation on foo. So when we run this code, now you're going to see the call to this, which is the specialized increase operation, which is this one. And that prints out that. And then it calls foos plus plus, and that ends up calling this. So this is a very comprehensive discussion of specialization where you can come along and explicitly instantiate the templates and specialize them for particular data types. And you can see how C++ templates do what's called duck typing, where they expect certain operations to be available. For example, in this case, you need to be able to plus plus an element. And if you don't provide those operations, then the compiler won't let you compile the code until you do something about it. And of course, as we saw, there's various ways to solve that problem. Okay, so that's the discussion about, that's the first discussion of specialization. Let me now go ahead and talk about another example. So this example is going to really show specialization on steroids. This is a really fun example. So we're going to have, this is what's called partial specialization. So far what we showed was complete specialization, where we took the container class and then we instantiated it with, int or double or char star or foo or whatnot. And now we're going to go ahead and show what's called partial specialization, which is another really cool concept. So to illustrate partial specialization, we're going to have an example class that's parameterized by type T and type U. And you can see the constructor for the example class is going to print out that it's parameterized by T and U. Okay, so far so good. Now what I'm going to show you are a bunch of partial specializations of this example class. And so you can see here's a version that has the same parameter for both elements. So the first and the second template parameter for example class will be restricted to be the same type. And you can see, we can tell that that's what's being used when you see example class T comma T. So you can see that's different from example class T comma U. So in this case, this version will be selected, this version of the class, the specialized version, a partially specialized version, will be selected when both parameters are the same type. The next example is yet another example of partial specialization, and this occurs when the second parameter is an int. So the first parameter is what's called unbound. It could be whatever you want. It could be a double, it could be a foo, it could be a char star or whatever. And then the second parameter must be an int. And so if that's the situation, this is the class that will be selected. And then the last example we'll look at for the moment, and we'll look at one more later. This one is one where we have two parameters that are different, and they are both, or they could be different, and they're both pointers to T. So in this case, we've got T star, U star. So if the parameters are pointers, then that's the one that's selected. So armed with those partial specializations, let's come down and take a look at the code and see what happens here. So here's the first instantiation of example class, and this instantiation is given an int and a double. And because that doesn't match any of the other specializations, the other partial specializations, it's going to print example class TU, which is this guy up here. That's the original unpartially specialized template definition. Down here, we're going to have B, instance B, be example class that has double double. So both of those things are the same. Well, that's going to match this specialized version where there's one type and it's repeated for both parameters. The third version we have here, as you might suspect if you're following along with the pattern, has some type, some unbound type, which in this case is double, followed by a bound type, which is int. And of course, that's going to match this specialization, which is T comma int. And then the final thing we have is we're going to have object D, which is going to be an example class instantiated with int star, double star. And that, of course, is going to print out example class T star comma U star. Okay, so that's just showing you how these specializations work. Let me run the code just to prove to you it does what I say it does. And voila, it does. So it's picking the different constructors to call based on the template parameters, which have been partially specialized in order to be able to narrow down and refine or customize the choice of which class instance to pick. So the last example I want to look at is what happens if we do example int. So that presents us, of course, with an ambiguity, because is that going to be the one where both parameters are the same, or is that one where the second parameter is an int and the first parameter is unbound? Well, that turns out to be inherently ambiguous. So the compiler basically says, sorry, I have no idea what you're trying to do here. It's an ambiguous partial specialization. I can't pick the right one. So it basically won't compile. So you might ask the question, how are we going to fix that problem? Well, it turns out it's very easy to fix that problem by defining yet another specialization. In this case, this is int. And so that will then take precedence over all the other versions, and you can see when I run the code that that's what gets printed out here. So it no longer is ambiguous because we've given it that extra specialization. So this is, I won't say this is super sophisticated, but it's pretty darn cool, and it demonstrates the fact that specializations can take place and that the compiler will pick the more specialized versions of things in order to be able to make the right choice. Okay, now, you might ask, well, okay, this is all really well and good, but when the heck is this ever useful? This turns out to be very useful if you have certain behaviors you want to have happen or certain optimizations you want to have happen for certain data types. So there might be situations where you want to optimize for ints or optimize for char stars or optimize for, you know, doubles or whatever you're optimizing for. And this allows you to be able to write that code to be very custom, and then the compiler will pick the customized version, giving preference over the more genericized version. So we'll talk later when we get into the innards of STL. STL actually uses this mechanism very, very heavily in order to specialize its generic templates for particular data types in order to optimize them more effectively even by doing things like using built-in compiler mechanisms for moving bytes of data around in certain situations. So it's super cool and certainly very powerful.